Okay, so today we're going to talk about two things. We're going to talk about an umbrella category for chemical reactions, and then we're going to get into a specific version of that. So go ahead and record this in your notes. If you need to pause the video, you can. So a redox reaction is any reaction in which we have electrons moving from an atom, and it therefore changes their oxidation number, their charge. So any element by itself has a charge of 0. Then when it forms a compound, there's an exchange of electrons and it gains a charge. So magnesium metal all by itself has a charge of 0. When I put magnesium in a compound like magnesium chloride, now it has a charge of 2+. So there are three reaction types that are typically going to be redox: single replacement, synthesis, and decomposition. Today we're going to focus on single replacement, and then in a few days we'll focus on synthesis and decomposition. So go ahead and write this down about single replacement reactions. If you need to pause the video, go ahead. So single replacement reactions are very, very similar to double replacement reactions, with the small exception of that we're not starting with two compounds. We're starting with a compound and an element. And that element is going to switch places with an element that is similar in the compound to form a new element and a new compound. Now, the thing that's tricky here is that it could either be a metal switching with a metal, or it could be a non-metal switching with a non-metal. It can go either way. All right. So on your worksheet for today, we have a spot for pop goes the hydrogen. All right, and there's a place to record the equation on the worksheet, pop goes the hydrogen. So if you will, write this equation down. And let's go ahead and actually write this equation and predict the products. So we have magnesium reacts with, that's our plus, hydrochloric acid. Okay, magnesium, metal all by itself, element all by itself, so we have to check the diatomics chart. Is it a Hofbrinkel? H-O-B-R-N-F-C-L-O? No, it's not a Hofbrinkel. So this is just going to be Mg. We're going to react that with hydrochloric acid. Is the first element a metal? No. Does it end with acid? Yes. Does it start with hydro? Yes. This is a binary acid, so we're going to put hydrogen, and then the other non-metal here is chlorine, Cl. Hydrogen is 1+, chlorine is 1-, so we don't even have to crisscross this because everything cancels out. Okay, so what's going to happen when I put my magnesium metal into the hydrochloric acid is that the magnesium is going to kick off the hydrogen. So it's going to form magnesium chloride and hydrogen gas. Okay? Now, we need to make sure these formulas are correct. So let's double check and crisscross our charges. So magnesium is a group 2 metal. It has a 2+ charge. Chlorine, we said, was 1-. So the 2 for magnesium is going to go on the chlorine. The 1 disappears because we are lazy and we do not write 1s. Over here, we have an element all by itself, so we have to check the Hofbrinkel list. Hofbrinkel starts with H. That's an H, so this is going to be H2. So then we need to balance our equation. We have 1 magnesium, that's good. 1 hydrogen, 2 hydrogen. So how do I make a 1 a 2? I'm going to multiply it by 2. We distribute that 2, so I have 2 hydrogens, but I also have 2 chlorines. I have 2 chlorines here, so this is balanced. Okay, so I'm going to put my goggles on, and we're going to do this reaction. Now, magnesium metal is one of my favorites because it's really, really reactive, okay? But not so reactive that it'll react with water. So I can actually pick it up and touch it with my hands, but it is going to react vigorously with an acid. So, how do we know that this forms hydrogen? Well, that's the fun part. Hydrogen is extremely flammable. So if this produces hydrogen, I can take that hydrogen and light it on fire and it will burn. So I I'm going to take some 3 molar hydrochloric acid. This is half as concentrated as what we did for the titration. And I'm going to put that in my test tube. Okay. Then I'm going to add a few pieces of this magnesium metal to it. And you'll notice that immediately it starts bubbling very vigorously, and we see this kind of smoky steam coming out the top. So let's test our steam and see if it's actually hydrogen. If it's hydrogen, this will burn. We got hydrogen. Now, watch this. I can't do it again because I've used up all of the hydrogen in the test tube. I've reacted it with oxygen in the air, and if you look at the test tube, you can actually see that the test tube has water droplets that have formed on the sides of the test tube from where the hydrogen reacted with the oxygen to form water. And if I touch this, it's quite warm. It got very, very warm. And if you look really carefully, you will notice that the magnesium is gone. Well, it's not really gone, but it's now in the compound magnesium chloride, which we all know from our last experiment is a water-soluble salt. So all that's left in here is magnesium chloride and water and some excess hydrochloric acid. So the next demo is called the Wimpy Can. And we're gonna go ahead and do the demo first, and then we will go over the equation for that one. So I have here a nice regular old can that I got from Mr. Bellin because he loves to drink sodas. And I am going to very carefully and gently just pull it in half. Now, I totally cheated, because I used a little reaction here. So if you look inside the can, you can actually see there are little brown chunks inside there, little brown chunks, and that's actually copper metal. So what I did was I took a metal file and I scored the inside of the can, because metal cans are coated in a plastic coating so that we don't leach aluminum out into our beverages. So I took this metal file and used it to make a nice circle around the inside of the can to get that coating off. Then I poured in a solution of copper 2 chloride. And the copper 2 chloride is going to do an exchange of places with the aluminum, making it so that all that's really holding that can together is the paint on the outside. And it makes it perfectly easy to just rip that in half. So let's do the equation. Okay, so that's called the Wimpy Can demo. You have somewhere to write the equation in your notes as well. So go ahead and write down this equation for what I did to the can. So I put copper 2 chloride solution with my aluminum metal, okay? So we have copper 2 chloride, the first element is a metal. There is a Roman numeral. Remember, the Roman numeral is the charge of the metal, so this is 2, so that's 2. Chloride, IDE, means we're talking about elemental chlorine with a charge of 1 minus. The 2 from the copper comes down to the chlorine. And then we have the plus. And then aluminum is an element all by itself. So we check our Hofbrinkels. Is an Al part of the Hofbrinkels? No. So we can leave it like this. So what happens here is that the aluminum and the copper are going to switch places. So we're going to end up with the aluminum and the chlorine together and copper by itself. Now we need to re-crisscross the charges. So the charge on aluminum we look up is 3. Charge on the chlorine is 1. So the 3 from aluminum comes down to the chlorine. The 1 disappears because we don't write 1s. Copper, not a Hofbrinkel, so we just leave it like Cu. All right, and then we have to balance our equation. We have 1 and 1, 1 and 1. Oh no, we have an ugly 2, 3. What do we do with an ugly 2, 3? We go to the lowest common multiple, which for 2 and 3 is 6. So how do I make a 3 a 6? I multiply it by 2. That also changes, remember we distribute, so that changes the aluminum to 2. How do I make a 2 a 6? I'm going to multiply it by 3. When I do that, that's also gonna make the copper a 3. So I'm gonna have to put a 3 in front of my copper as well. Okay, so the rest of the worksheet is your homework. Make sure on the back, you're just finding the 3 single replacement reactions. Circle those and then balance those.